For more videos like this for Discrete 1, you can take a look at Sarai Studies, link is in the description box below.
In one of the previous videos, I introduced what a compound proposition was. I just never introduced a symbol for it. So the symbol is this. We pronounce it as phi. And anytime we write this, is saying, hey, we have a compound proposition made up of these variables p and q, and one could be like p and q. So this is a compound proposition made up of p and q. And what is it? It's p and q. That's how we read that. So compound propositions have certain properties. You can check if a compound proposition is satisfiable or if a set of compound propositions are consistent. So the definition of a compound proposition, phi, made up of any number of propositional variables, is satisfiable if and only if, so no, anytime we have a proper definition, discrete, it has to have if and only if, there is at least one truth assignment of the propositional variables, of these variables, from the first variable to the n number of variables that make the compound proposition true. That doesn't make sense? No problem. Let's do an example to put this into perspective for you. Here we have, is this compound proposition made up of these two variables p and q satisfiable? So first you want to do a truth table. How many columns? Well, you have 1, 2 variables, 2 propositions, so we do 1 for each of our propositions, and then we also do 1 for the entire compound proposition. And instead of writing p and q, we can simply just write phi, the compound proposition. Remember that the number of rows is equal to 2 to the n, where n is the number of propositions, number of variables that we have. We have 2 of these, so it's going to be 2 squared, which is 4, so we're going to have 4 rows. How do you fill in the truth table? You want to take your number of rows divided by 2, write it down below in the first column, and then keep dividing by 2 until you get to 1. This tells you how many trues and falses you're going to have to start off with. Again, you want to start with trues. I'm going to do 1 true, 2 trues. I'm done using up all my trues. Then I move on to my falses. 1 false, 2 falses. I used up all my falses. There's no more space left in the column, so I move on to the next. Here I'm going to have 1 true and 1 false. So 1 true, 1 false. I have space left. What do? I copy and paste the exact same pattern that I already have written, which is just true and false. I do it here again. Now the compound proposition is p and q. Remember, with an and, this is only true if this and this are true. So the only way we will get true is if both of them are true, and that's only in this case. Everything else is false because there's at least a false in each of those. Now by looking at the truth table, you can tell if this compound proposition is satisfiable. So there is at least one truth assignment of the propositional variables p and q that makes the compound proposition true, and that truth assignment is where we assign p to be true and q to be true. So we say yes, this compound proposition right over here is satisfiable. In other words, a way you can think about it is that it can be satisfied, it can be true at least once. Because I see that it can be true at least once, then it's satisfiable. Let's try another one. Here we have the same number of inputs, so it's going to be the same truth table in terms of the individual propositions. The only thing that's different is that we have another compound proposition. Let's call this 1, let's call this 2, so we can differentiate here. And this one is p and not p. So to make our lives easier, let's do another column for not p. Not p is just a fancy way of saying the opposite of p, so whatever p is, we just take the opposite, so that would be false, true here, false here, false here, true here, false here, true here. And then our compound proposition is p and not p. Again, an operator, that means that the only way that this is going to output true is if this and this are true at the same time. So p and not p should be true at the same time. True and false, that gives you false. True and false, that gives you false. False and true gives you false. False and true gives you false. All of them are false. And so in other words, the compound proposition cannot be satisfied. It was never true, at least once. But think of satisfied as just being true. You're just looking for when the compound proposition can be true at least once. If you're told to show that a compound proposition is not satisfiable, that it can't be satisfied, then you have to show that all of the possible truth assignments, they're never true, that they never can be satisfied. You can't just show these 3 and say, yeah, it's not satisfiable. No, because this one can be. You have to show me that it can't. Because the definition of a compound proposition that is satisfiable is that there is at least one truth assignment of the variables of the propositions that make the compound proposition true. So if you didn't show me this one, then this one could be that one truth assignment of the propositions that can make it true. You have to show me that it's also false, and then I'll believe you. Let's try one more. Here the question is this compound proposition made up of these propositions or propositional variables p and q satisfiable? In other words, can it be true at least once? So let's look at the truth table. First of all, there's only 2 propositions, 2 variables, so it's again going to be the exact same number of rows, but I need not p and not q, so I'm going to make a column for those as well. Here we already did not p, it's just the opposite of p, so if p is true here, it's going to be false here, true here, false here, false here, true here, false here, true here. Opposite of q is literally the opposite of q, so true here, false here, false here, true here, false here, false here, true here. And then we also need to know the truth values of these compound propositions. So let's go part by part. Let me do this one here, P or Q. This is an OR operator. Remember that with an OR operator, it can only output true if this or this is true. So only one of them have to be true. So we're just looking at our truth table and we're just looking for one of these propositional variables to be true. So in P and Q, as long as we see one true, the whole thing is going to be true. One true, whole thing's true. One true, whole thing's true. Here we see no truths, it's going to be false. So that's this one. Let's move on to this one. This is not P or not Q. Again, or operator, we're just looking for one of these to be true, then the whole thing is going to be true. So we're looking at these two columns, not P, not Q. Remember, I'm looking for at least one true. I see no truths here, so this entire thing is going to be false. I see one true here, true. One true, true, true. And now finally, we need one column for this entire compound proposition, which is this and this. So I can do 5, 3, or I can literally write this here, or I can label this column as 1, this column as 2, and do 1 and 2, which is this here. However you feel like doing it, but I'm going to stick to what I've been doing, which is just compound proposition 3. So this is an AND operator. That means that this and this have to be true in order for this to output true. So we're looking for two truths. I don't see two truths, so false. I see two truths, true. I see two truths, true. I don't see two truths, false. Now, can you say that this compound proposition is satisfiable? In other words, you're just looking for when it's true at least once. So you can say, yes, it is satisfiable because you see that it's true here and here. So there is at least one truth assignment of the propositional variables P and Q that makes it true. And those truth assignments are these and these. So P can either be true and Q can be false, or P can be false and Q can be true. But if you're answering this question, is it satisfiable, and you're doing the truth table, you can just stop after you see this one, because you only need one to prove that it's satisfiable, to prove that it's true at least once. You only need to see it at least once. If it asks you for all satisfiable assignments, then you would have to go through the entire truth table and find all of the possible truth assignments of P and Q that makes a compound proposition true. So here you could say the satisfying assignment is PQ is equal to true, because that's what it is. P and Q are true. That gives you the compound proposition as true. And here you can say a satisfying assignment of P and Q is when P is equal to true, so P is equal to true, and Q is equal to false. That gives the compound proposition as being true. So to summarize, if they're asking you if a compound proposition is satisfiable, you're really just looking for at least one row where the compound proposition is true. Here we had at least one where the compound proposition was true. Here we had at least one where the compound proposition was true. You only need to show one to say that it's satisfiable, that it can be satisfied, that it can be true at least once. Here we had none, so the compound proposition is never satisfied because it's never true. And that's it for part 1 of this video. In part 2, we'll talk all about consistency.